Thank you all for coming, spending the very last session of your conference talking about this. What we're going to do is we're going to look at NoSQL databases. We'll do like a quick flyover of what does the landscape of different type of NoSQL databases look like? What are your choices there? We're going to spend the majority of our time talking about document databases. You guys, how many of you came to my previous session? A couple of you, okay. So in there, I'd already said that I think these document databases represent your sort of best chance at having something that is both embraces the NoSQL philosophy and some of the features there, but can also serve as a general database. So for example, there's graph databases, but they would be a poor choice as a general purpose database. So what we're going to spend a fair amount of time on are the document databases, because I think they're most broadly useful. Okay. All right. So like I said, we'll talk about the general story behind them, and then we'll look at sort of four major areas where you make important choices about performance and so on. Okay. We're going to talk about document design. We're going to talk about indexing. We'll see that that's even more important in NoSQL databases than it is in regular databases. We'll talk about certain types of operations that you can do on the server, kind of set-based things, as well as the scale-out story on NoSQL. Okay. So quickly, here's Michael's definition. My personal, I just made this up out of thin air, definition of what NoSQL means. But let's take a step back just for a second and think about the history of where the term NoSQL came from. So NoSQL does not mean not only SQL. You'll hear people say that. Something of a, hey, can't we all just get along and not ruffle the feathers? And that's a great worldview, but that's not where the name came from, right? Like I said yesterday, I have a toaster in my kitchen. My toaster doesn't use a relational database or SQL. That doesn't make it a NoSQL toaster, right? Okay. It just doesn't tell you anything to say, well, we can have choices. Yes, you can. Now, what is it you're talking about? If you look at the history, back on June 11th, 2009, a bunch of people who were sort of thinking about scaling, horizontally scaling databases, got together in San Francisco. And these are like big table people from Google, Cassandra from Facebook, and those types of guys. They were all thinking about, well, how would we redesign and reimagine a database if one of our key goals was simple and easy horizontal scalability? Right now with relational databases, you can do that, but it's very difficult, and a lot of that happens in the app. All right. So back during this meeting, one of the guys who was attending said, hey, we need a way to refer to this on Twitter, because that's really how you have a legitimate meeting if you can speak about it with a hashtag, right? So somebody came up with the term hash NoSQL, and that's where the term came from. Right. So my definition, sort of inspired by the original meaning of it, is NoSQL systems are databases where they are basically built to be cluster-friendly or horizontally scalable-friendly, and they give up certain things like joins across records and certain types of transactions in order to make this horizontal scale one of their primary features. Okay. So there are actually four types of NoSQL databases in the general industry, if you think about this, but only three of them land in my definition. Okay. So the simplest, most low-level one are these things called key value stores, where you can basically query something by the primary key, and you get a blob of whatever you want back. It could be text, could be binary. The database doesn't know what that is. It's just, here's a blob of something I serialized, and I want to be able to access it by primary key. Right? So this includes things like Amazon DynamoDB, which is a pretty awesome system. Have you guys ever looked at Amazon DynamoDB? It's interesting because you don't pay for it in terms of usage in the normal sense. The way you pay for it is you say, I have 100 gigabytes of data, and I need a response time of less than 10 milliseconds. They say, OK, that costs X, because they'll just give you enough hardware in horizontal scale until they can guarantee less than 10 milliseconds for that amount of data. One really interesting announcement there, by the way, is this week, last week, within the last week. They basically said, we're going to support rich document JSON type objects with nested queries and indexes, which is, again, a document database. So Amazon DynamoDB basically also just jumped here into this world if you're interested. Okay, other popular ones are like Redis and Rake and so on. We also have what are called column store databases, and that's Cassandra and some others. We have graph databases like Neo4j. The J stands for Java, but you can access it from .NET and all sorts of languages. And then we have the document databases, CouchDB, RavenDB, and MongoDB. We're going to talk about Mongo mostly. I'll show you why if you guys haven't seen that. But first, let's look at the difference real quick. So here's what a key value store, looks like. Right? I've got some primary keys. I can do queries on that, and then I have data. And that comes back when I do the query. Now, you can do things like add metadata and then do a query on the metadata, but you've kind of got to put that in extra. It's not just part of the data. Okay? Obviously, this is super fast and very easy to horizontally scale, right? Because all you've got is a bunch of primary keys, and if one's over there and one's over here, you could do that on like a range-based distribution, or it'd be insanely easy to horizontally scale that if it were integers, right? But it's very low in the sort of flexibility that it has. You can't do big data type questions on this, right? If you need really interesting queries in here, how are you going to get them, right? Probably you're not. We have the most bizarre of the databases, these things called key value stores, where I've got some sort of primary key, and I've got columns that look normal, like these up here, right? That's like any regular database might have that along with a primary key, but then they also might have what you would think of as kind of a pre-joined other set of related items. All right, so I could go and get the user and all of their orders in a single primary key query, which is just kind of funky, but that's how it works. Now, we also have these graph databases where basically what you store and query are the relationships. Right? So I might store Joe and Sarah and Pierre and Michael and so on. I also might store electric things that they're interested in, like Teslas. Well, I guess Ferrari's not quite yet, follow Lamborghini maybe. But, right, so we know that maybe Michael would like a Tesla or a Volt, but those things are expensive, so whatever. I'm friends with Pierre. He has this type of electric bike. And so these are the relationships you can model, right? So this, according to my definition, does not work well for a NoSQL database. Right? It lands under the not SQL banner. So you hear it get listed a lot, but this is very cluster unfriendly. The more pieces are connected, if you try to put them on different servers, you end up with IPC and coordination, and this is super hard to horizontally scale. So let's look at document databases. How do they work? They basically take objects, whatever your in-memory entities look like. Here we have, this is actually out of Developmentor's, where I work. Out of Developmentor's course catalog, we run all of our infrastructure on MongoDB. So if you go to our website, you're using Mongo in some indirect sense. This is actually right out of our course catalog. And so we have a course, and it has normal columns, these are all just sort of straight values that you might have in SQL Server. But then it also has engagements, which are like classes that we run of that course, right? So we might run one, I don't know if it even says where, it doesn't say, I put ... right, so it would fit. Maybe this one is in Los Angeles, and this one is in London, and so on, right? But instead of storing these in separate tables and doing some kind of join, in document databases, you can sort of embed these other rich documents. Right, so here we have, right, what does that mean? Sorry, square bracket, Java, JSON? Array. Right, so we have an array of open curly, close curly, that means object. Right, so we have, instead of having a course table and an engagements table and some sort of normalization, or at least a foreign key one-to-many relationship, we put these inside here. So what's the advantage? Well, if you're going to look at the course page, you probably would also like to see what classes are coming up. Maybe you want to take them, right? We don't have to do a second query back to the database. No joins, nothing. Technically, we do a index query against this field, URL path, right? Because that's sort of actually, we're not using IDs in our URLs, we're using just names. And then this stuff just comes along for the ride. Does that make sense? a little bit of a different world. Now you'll notice, we already talked about JavaScript all over the place, right? Opening object there. So you'll see that these things are represented to us as human beings as JSON because we don't read binary, but that's not how they're stored in the database. They're stored in something called BSON, which is like a tokenized binary representation. They have types. Like, for example, this is a date time. These are object IDs. These are strings. Those blue ones are Booleans, so on. Right, so there's actually types in the sort of database kind of implicitly. OK. So these all look to be really different. But if you look at it in the right way, if you look at how are these things cluster friendly or unfriendly to some sort of horizontally scaling, the first three are actually fairly related. Right? They all have natural aggregate boundaries. Like in our course example, our course is the aggregate, and it happens to have things like the engagements. And there's other stuff that wasn't shown there, all like wrapped up. So I get that aggregate out of the database. And those become really good for horizontal scaling because you typically don't need two aggregates at once. You just need one document and its sub-pieces or another, and it's easy to put those on different machines and do interesting stuff. Similarly with the other ones. Relational databases are somewhere less related to aggregates. And then way down here on the very scattered, disorganized, hard to separate is the graph database. Right, so that's why I think these really fall under the NoSQL banner. All right, so let's look at something concrete here. So let me pull up a website, and then I'll show you what I'm talking about here. Hopefully the internet cooperates. So we have at Developmentor an online training system here. And where do I want to go? Let's just go here. So you can take these classes, like for example, here's an HTML5 class. This, of course, like I said, is running on MongoDB. And we have these lessons, right? So like here's a lesson about geolocation. So let's go look at that for a second. Now, there's a lot of stuff going on this page that in a relational database means there's lots of joins and scattered bits. And we originally did this on Entity Framework. Let me zoom this a little so you can see better. We did this on Entity Framework, and we had lots of joins. And we ended up just doing caching of our in-memory entities and then sort of managing the cache. So you've got stuff about this. We call these tasks. So we got stuff about the task, like its name, its time. These are like flat entries. We also have how many people have voted this up or down, if they favorited it, what are the tags, what are the objectives, what are the related tasks that you might need to do before you do this task, what are the activities. You go into the activities, how long are they, what are they made up of, and so on, right? So we were not particularly happy with how this was working in Entity Framework plus SQL Server. And if you look at the database diagram, I think this is from the Entity Framework Designer in Visual Studio. You can see why. Like, see all those relationships? Those are the tables we have to touch to show that page. That was wrong. I mean, possibly we rework our database to be less normalized. But this was sort of the natural breakdown of these things. And it was not pretty at all, right? So tasks are related to activities. They're related to tags. You can vote on both activities and tasks. And just like, this is wrong. So how would this look in a document database? Now, before I show you, it's worth pointing out that the title of this talk is about performance. But the reason that you guys care about document databases in general and MongoDB, because it's the best choice of those types of databases, is because things get simpler and easier to manage. And it happens to be free and faster, and these are all great. And we'll talk about the scaling. But the primary reason that you care about these things, I think, is really simplicity. All right, so we were working with this, and we were fine with it, but we didn't love working with it, right? So we said, well, how does this look if we use this in documents? Well, that's the new diagram in MongoDB. Which one do you think is easier to reason about? Right? Which one do you think is easier to scale? Like, look at the relationships. No relationships there. Whoops, wrong direction. Many spider web sort of relationships here, right? And that's why the horizontal scaling is super easy. Now, that doesn't mean, this is the model here, but it doesn't mean we just have 3 classes or 3 entities involved. We still have basically the same classes involved. We just work with them differently. So for example, the task embeds activities. The activities embed like votes on the activities and such. Right? He votes on the task, and here there's also votes on activities and so on. So there's all these classes, but the ones with the squares, the black grayish squares, those are the aggregates. Right? Those are the top level things that we have, what you call collections in MongoDB. Same thing as tables, but they're not square, so they don't call them tables, they call them collections, right? But those are the three collections that you saw, but they still do have these objects, right? Like the task has activities and they have types and whatnot, but they're sort of embedded. So when you change your model to look like this from this, you're making different choices about optimizing whatever. Here, you're optimizing disk space and repetition of data and these sorts, like minimizing repetition, optimizing disk space, those kinds of things. Over here, you're optimizing sort of performance and simplicity. So when you think of those arrows, those are pre-computed joins that we always live with in our new system. Right? When I get a task, I always get the activity and the votes. And it's not a join I do in the database. It's like basically pre-computed and stored that way in the database. All right. What's really interesting about this in the document database sense is I can still do ultra high-speed queries based on these sub things. Right? So if I were to go make like an XML element in a SQL Server column, I could put stuff in there, but I can't really query it in the same first-class way I could other columns in SQL. But you'll see in Mongo, I could go and create indexes on parts of that thing and still do those queries. Right. All right, so why Mongo rather than something else? Go kind of quick through this. If you look at the various choices you have out there for NoSQL databases that are pretty popular, there would include probably CouchDB, RavenDB, Apache, Rake. There's others we could put up there, but the major document databases are up there. One of these graphs is unlike the other, right? Which one would you bet your company on? Or your project or whatever, right? There's dramatically a bigger ecosystem and set of tools and open source, whatever, and people who already know how to work with this thing if you choose Mongo over pretty much anything else, right? So that's why we're talking about it rather than Couch or Raven or something like that, right? But still the ideas are basically the same for documents. So we're going to talk about 4 ways we can make this fast and sort of things we have to consider when we're thinking about performance. And the most straightforward and simple way, the place to start is how do you model your documents? So if I go back a couple here, we said we're going to model our particular page there so that we are pre-computing these joins, and we're making the assumption that when I get one of these tasks, I'm almost always going to need information about the activities that make it up. Right? Maybe I need to say what types they are. Maybe I need to say how long they are so I can sum them up to be how long the task is going to be in sort of time or whatever reason I need them. But I need these things when I get the tasks. They're most useful together, or most of the time used together. Does that make sense? So when you think about how do you take your entity model and break it up, so we could have easily had a task with some IDs that pointed to an activity table, but we didn't. Because in our world, almost all the time when we get the task, we want the activities. If your world, you didn't do that, you might put them separate, right? So I'll refer to that as normalizing, even though there's not technically a foreign key relationship there, right? So we'll call that normalizing versus embedding, okay? All right, so you want to set up your system so you're doing as few queries to the database as possible, right? And you also want to set it up so your documents are not too gigantic, because if you're dragging hundreds of megs across the wire off disk just because you want some single value, that would be wrong, right? So don't do that. All right, so let's go and write some code, because I don't think you really learn a whole lot unless you see a little bit of this in action, okay? Some of this stuff I got pre-built, and we'll just run it and see it going. But let's, just because I know that 88% of you guys have not done MongoDB before, That's just an estimate. But a majority of you haven't, right? So let's just do a little quick bit of, hey, how do you do this? How many of you guys are familiar with .NET? Is that a reasonable language for you? Are? Okay, cool. Then we'll get with that. So we start out by creating some new project. It would probably be a website, but because this is like a super simple demo, it's going to be a console app. Right? But imagine cool web stuff happening that we're not going to see. Now, you start out by going over here and you say manage, let's do it on the solution, manage NuGet packages. And you go online and you type MongoDB. And you love to see the internet work. Fantastic. Okay, so I've already downloaded this because I know the internet may not work at conferences. This happens, and it's really bad if you don't prepare for it. But you can see there's many, many pages of stuff about MongoDB, right? And there's more than you see there. It just happens to be 5 is all they show in the little UI. But you want the official C# driver for MongoDB. And this is an open source thing. I can go to GitHub. And I come over here and I can search for MongoDB. In fact, you can see here's Craig Wilson working on some new stuff for the driver. These are and Robert Stam. These guys are both on MongoDB. And I could just probably jump over there, right? No, they're on their own branch. Anyway. MongoDB. You know what? How about just MongoDB? So they've got the database is open source. You can download it. It's written in C++. They have C, Perl, Java, C# driver. This is the one we just saw on GitHub. Right? So you could download it if you want. But we're just going to say, install. Right? And the other thing we did to make things simpler is I wrote a layer on top of that that will basically add optimistic concurrency, the same that Entity Framework has, for making changes in ORM style. Right? And I'm happy to talk about that in more detail if you want, but we're not going to do a lot with that, just sort of leverage some base classes. So if you install that, then you can go over here and create this class, which should look a whole lot like what you get when you do Entity Framework code first, because the Entity Framework guys were super inspired by this model. Right? So what we're going to do is we're going to write some classes, and then we're just going to push them into the database. Okay, so I can come over here and say, look, I want my database to be called this, SA perf design. Keep that, remember that. And then I'm going to have iQueryable properties that I can do link against. Right? So that's pretty awesome. Let's go over here. And I made a little class. So we're going to have 2 classes. We're going to have books, and we're going to have reviews of those books. So I just want you guys to quickly see, like, what does it look like if we put it inside the book? What does it look like if we put it outside the book? And so on. So over here, in order to put one of these classes into the database, first it has to be like a meaningful class that you care to save, right? It has to have data. So you'd want things like a string, I would name, maybe ISBN, maybe a date, time, published, right? Like that. And it needs a primary key. In MongoDB, the simplest one is this thing called an object ID, which is very similar to a GUID, like a GUID, right? Generated in the database. It manages certain things so that if you do horizontal scaling, it won't have conflicts across machines, things like that. So we have this. And then we can go over here and say, you know what? We also have a list of review. And call that reviews. And let's just go down here and say this has a string, whatever that is, string user, right? And maybe it has something else like a date time. Date, so it has like some meaningful data, right? Created. Now that's good. And let's just make things a little bit simpler on ourselves and say, anytime you create one, it's just going to be now. The database will replace it with the value if you get it out. But this way, when you create a new one, you don't forget to set the date time and go, oh, why are none of our queries working where we're looking for the current reviews? Oh, because we've been running for a month without ever setting the created time. Great. That's awesome. That's never happened to me, of course, but I hear it does. So if you guys know Entity Framework code first, the way that works is you sort of create these classes, and then you interact with them, and it will go and generate the database for you. And it'll create the tables and the relationships, and it'll say, okay, well, there's a review, and this list must be a one-to-many relationship between books and reviews, so we'll create that relationship and the other review table. And that's all glorious and beautiful until you make a second change, right? Because the second time you're into migrations and update scripts and push, moving forward, moving it back, and you're still in this relational model, which is not amazing. So let's see how this works in MongoDB. So let's go over here, and I'm just going to make a book. So we'll say book B, new book. Let's set some stuff about it. Let's say it's ISBN. Well, what do you guys think? Book right? I'm sure there's an algorithm that would tell me that's perfect. Okay. Set the name. This will just be Harry Potter. I don't know why that's stuck in my brain lately. Published equals date, time, dot. We'll just say now, but it could be some other time. Right? And reviews, let's give it some reviews. Now, I'm going to show you something that's going to crash so that you appreciate what I'll do next, all right? So let's add some reviews. We'll say a new review goes here. Let's do a cool little object initializer thing. We don't need to set created. Let's just say user equals Ted. We'll add another one for John and one for Sarah, or something like that. All right, and then I'll go var Mongo equals new MongoDB data, what do I call it? Mongo context, sorry, Mongo context. Mongo.save. Book, yeah? Make sense? This should look pretty familiar to you guys. Let's do one more.
Does Mongo implement idisposable at all?
No, it doesn't maintain connections. It has a connection pool. The driver has a connection pool, but it's not a stateful. It's not, you don't like open connections and work with it, so you don't need to really do idisposable. Yeah, it's a good question, but they don't have it. So say Jeff is going to review this one, and also Sarah. And this will be Harry Potter 2, which obviously means that's a 4. Just so we have more than one record, so you can actually do a query and see anything happen at all, right? Okay. And let's go and say mongo.save B. Now, let me open up the most awesome tool for working with Mongo, this open source free thing on GitHub called Mongo, RoboMongo. So I'll go over here, open that up. And notice, if I zoom in, whoop, we have a bookstore, which we're going to work with later when we look. This has like millions of records, and we're going to play with that in a little bit. This is the learning line stuff that you guys saw, right? Those, like, for example, I was telling you about task. There's that, right? And some other stuff. And then here's our develop.com website. But what you don't see is software architect performance database, right? None of that. And you also don't see me opening up some kind of design surface where I like spec out the columns and the shape of none of that. What I have done is I've just defined a couple of classes, and I'm going to tell them to be saved in the database. So what will happen is I've hard-coded the name of the database that I want here, but it could come out of a config file or wherever, right? So it's going to look and says, does that database exist? No, let's make it. Is there a thing called book, a collection? Nope, let's make that. Now let's start saving things into it. So if I run it, I have MongoDB running as a Windows service. Object, yes, hold on. I have MongoDB running as a Windows service, so this should just work. But remember I said this is going to break. This is what it breaks. See this null reference, object not set to a reference? Do you guys know where that happened? This is the quiz. You get extra credit if you get this part right.
Is it the list?
That is the list. Extra credit goes to you. Perfect. So if you look over here, this is the most natural way to use it, not if reviews is not equal to null. If it's null, initialize, that's super annoying. So don't do that. Just go over here to the book and say, you know what, the book has a constructor. And basically, for all of your lists, just do this. When this is like that. Yeah? That way, when you first create it, you don't have to check are all the properties null and whatever. So now it runs, and it says pressing the key to continue. This is a very Unixy-like application. No output means, yay, it worked. So now let's go over here And if I do a refresh here, you'll see there's now this database. And if I look in the collections, you'll see there's now a couple of records. And if I show them in this view, well, they look very much like what you guys might imagine they were going to be. Does that make sense? So this is a super simple example. But take inspiration from our learning line thing, maybe. This is a really important choice about how do I store these in my database. Do I put them in, embed them, or do I have a reviews table collection and a book collection? Right. One is a little bit more work than the other. Not a lot, honestly, but a little bit more work. But it's always a couple of queries from the database, and it's going to be slower, usually. But on the other hand, if I most of the time do not want the reviews or need them, then all of a sudden, when I get the book, I'm bringing all this extra junk along. And these documents have limits. The limits are not really a database story. They're actually implemented in the driver because this is here to protect you, not the database. The documents they're not allowed to be larger than 16 megabytes. Because if you write a super simple query based on a primary key and you're pulling 100 megabytes off a disk, and you might start wondering, like, why is this slow? It seems like just this is an index query. What is it, right? So it's there to help you not get completely out of control. Right? So for example, if that list of reviews was unbounded, it could grow infinitely. Putting it inside would be a really bad idea because you could exceed that 16 megabyte length. It's highly improbable, even on Amazon.com, that would really happen. So maybe this is a reasonable approach, right? But you want to think about that. If you were doing analytics, for example, and you had a popular website, and you were storing information about every single view, and had the users and all, and you're like pushing that into a list, that would eventually be a problem for popular pages. Okay, so that's cool. Let's see how it would look if we did it the other way.
Quick question.
Yeah, go for it.
What's the connection string there, then? How does it know where the Mongo database is?
So what is the connection string, basically, is the question. So this, if you go over here to this guy, this base class that I wrote, if I go disassemble that, oh, cool, it's even in the same place on this machine. Okay, it somehow found it. That's nice. When you put this in, it creates a connection string that looks like this. Mongo, server name, port name, database name. And you can put question mark replication set, username, passwords, read preference, like all sorts of stuff. My library doesn't support it because I was lazy, but those connection strings can be really interesting. Let me just show you one more time. If I go here, you'll see the defaults that are just built into C#. Safe mode true, port, whatever, local, and that's where it runs, right? It's like, I forget the port that SQL Server runs on, but whatever it is, that's the, right, it's just like that. Okay, so let's look at this the other direction. Now you might think, first of all, there are no relationships in MongoDB at all, right? This is only at the application level. But how would this look if we split this? Let's go over here and let's duplicate that. And we'll just call this book 2. And instead over here we're going to have an object ID, which will be the primary keys of the reviews that are going to be in a separate table. So this is just like a sort of foreign key type thing, but it's not enforced by the database. Right? So here we'll call this review 2, but doesn't, well, yeah, we need to call it that. And since this is going to be a top-level type, it's going to need to have a primary key, so now I can get it out. It wasn't necessary before, but it is now. It might have been useful before, but it's absolutely required now. Okay, so let's go and rerun this code. And then we'll do just a really quick query just so you guys know what this looks like. So let's go over and say book 2. And instead of doing this, we really need to create the reviews first. I'll just do this for 1. Okay. And then we'll say Mongo dots, whoops, it's kind of out of order. Mongo.save R. So the way it works is the primary key will not be set until after you save it, right? So if I want to put its primary key into this list, I need to have saved it. Does it make sense? ID. Almost. If I had, oops, put it like this. If I call that review 2, I would have this. Make sense? And let's put this up here. It's going to be a little funky looking, but it's all right. Let's set the values, like so. And then let's just do a few more reviews, like so. That almost worked. So let's just do John and Sarah. Make sense? So let me just run that really quick. It should insert it into the database. If we come over here now, you'll see there's more stuff. There's a book 2, and you can see we just have these. I did miss a key point here, didn't I? As in, I forgot. Yes, b.reviews.add.r.id. Need that a few times. So just so we don't end up with multiple pieces here, let's just delete those. Perfect. Okay, so refresh that again. Now as we go look at this, you'll see here's our one book, and just let's look at it like this, with its 3 object IDs. So you might think that what we're going to run into is the dreaded N+1 performance problem of ORMs, where I get one item and then I try to like loop over the sub pieces, and for every one in its sub list, I got to go back to the database. Not exactly. So let's go and write a little link query now that this is all done. Just leave it in here for you. So let's say var b equals, we'll say, I need my Mongo thing, so var Mongo equals new, Mongo context. We'll say Mongo dot books dot where, let's say b goes to b dot title, is it name, equals Harry Potter. So if you guys are thinking this whole NoSQL thing is like completely crazy, this all of a sudden should look really comfortable, right? You guys know link. In fact, I would challenge you guys to somehow distinguish that from Entity Framework if the name of the class didn't really give it away, right? Like you couldn't distinguish the two. But this is actually going to translate into a different type of query. Let me just show you what the query syntax here looks like. Is what you do is you give it prototypical JSON objects. So I could say name, colon, and then I would say Harry Potter. And if I have 2 properties I want to get a match against, that's like an and. Then there's special syntax for or. So if I run this, notice there are 1 record. Well, there's really only 1 record in there. But if I run it, still it finds it, okay? So zoom out. So this will convert to exactly that same query. Just like Entity Framework converts to SQL, this converts to Mongo syntax, okay? And I could even do burst or default or singular default, take your pick. And it's saying, you could simplify it like this. Right? That's ReSharper trying to help me out. Then I could just say print, how about console write line, b.toBSON document .toString. Well, toString's implicit, right? This is just a MongoDB function that will turn it to JSON, so we can just easily look at it without me doing work. There's our Harry Potter. Make sense? So the performance bit. How do we get to the reviews in a reasonable way? So here I would say var reviews equals Mongo dot, let's say review, actually, let's go over here. There's a bit of a problem here. So we need to have this as books too. We're not working with the right type exactly. It's kind of durable enough to deal, but review 2. Oops, wrong direction. Thanks for the help. Review 2. Okay. So then I come over here, because I got to have the thing to do the review on. I would say dot where R goes to B dot review IDs. That needs to be 2. Review IDs dot contains R dot ID. Make sense? So then it does basically an in query on the set, and passes it over. And of course, I'm not writing them out, so let's just print those out. See if this will work. Should I like it? Yeah, it doesn't really. I guess I could say for each one, right? Let's just say of 0. How about dot first? Or convert it to array, take your pick. Make sense? So it's always 1 or 2 queries. It's not n plus 1, which is sort of what you'd be afraid of with lazy loading. But this is not lazy loading. This is Michael typing out the loading, right? This is explicit. OK, so that's the first item. You know, how do we think about modeling our data? Do we take our items and we embed them? Or do we put them in this separate, normalized, sort of separated table, connected with what you might think of as soft or weak foreign keys? They're not enforced by the database, but they are representing relationships, right? So, you know, do you usually want the reviews when you get the book? If the answer is no, then don't do this. It's just going to make it slower. But if it's yes, then maybe. So here's just an example of what you guys saw. If we embed it, it becomes like this embedded object. If not, there's just IDs or something. And the rule of thumb beyond just the do you use it frequently together is if it's unbounded or really large, never ever do this, right? Because of the 16 megabyte limit, which is there to keep you safe from yourself. Make sense? Questions before we move on? Yes?
With the, can you store, say if you go like scan documents,
Yeah.
you want to store in
Maybe they're 100 megs? Yeah.
do you-
Sure. So there's a separate thing in MongoDB called, let me see if I can get over here, if I can say this.db.gridfs. Gridfs is sort of a file system in the database, and you can just upload and download and delete and update files. And they can be arbitrarily large. They could be a terabyte. And it will break them into 256K chunks and put them across maybe even like a sharded cluster. But the cool thing about that is when you run a backup of your server, you get the files as well, right? But they're sort of optimized for reassembling and streaming them back out. We actually do that at Learning Line. If you go over here, this user bit, you can see this FS files and FS chunks. This is not the real one. The real one is like 20 gigs or something ridiculous. But you can see that it has this little file data bit with binary, and it would just break it into as many pieces as it needs to. Yeah, great question. OK, let's go back over here. So you might think, oh, yeah, go ahead.
Just enough, say in a web API application,
Uh-huh.
would you separate concerns between JSON and the VSON?
Yeah, so the entities you return over a web API response, are those the same things? They're probably different. I mean, if you've got to do this join thing, maybe that's not the right way to return it, so you're going to create like a DTO style thing. We've got several APIs we work with. One of them we actually return the Mongo objects and they just serialize fine and it's good enough. And others we have like transformation that happens on the server. So I think you want to think is the thing the client's going to get back reasonable to them or not? And basically you can treat the object IDs as strings on the JavaScript side, right? These just become like the strings of the numbers. OK, let's see. So you might think, right? You might be thinking, OK, this is like embedded XML types in where I can technically do an XPath, but how much performance can I really get out of that? So let's just take a quick look. Right? Like if you're thinking, like, OK, I've got a book. Bring that up one more time. I've got a book. And the book has an array of ratings. The ratings are custom embedded objects. The embedded objects have user ID properties. What if you want to know, what are all the books reviewed by user 3? What type of query do you write? What kind of performance can you get with that? So, if you couldn't reach down and index these sub-documents in interesting ways, you would get really bad performance, right? You would scan like gigabytes of data, and that would be wrong. Let me show you. Doesn't really matter. I guess I can do it over here. Doesn't matter. They're all the same. By the way, cross-platform, RoboMongo, that's kind of cool, if you care. So over here, we have this bookstore, and let me just go look at the collections. We open the books, and I can ask how many there are. If I ask count, you'll see there are 271,000 books. Within these books, you'll see each book has these ratings, and each rating has sub-objects and these values here. So let's look at this for a second. Let's try to answer the question, how many books were reviewed by this user? I have no idea who they are, but whatever, right? We're going to take that. What would we possibly write up here? Well, in Mongo world, what you write is you would say, I'm looking for, go to the object and go to its ratings array, and then go for each one of those, look at its property called user ID. How's this going to come out? Perfect, right? And match against this. In link, I would say, give me the book where b.rating.any r goes to ID equals this, right? It's a very simple link query. So if I run this, the very first time I run it, when it's kind of not awake yet, see that number right under find? 6 milliseconds. That's because it had to read it off disk. 0 milliseconds. We're querying over 1 million nested objects within the 250,000 books. And we know that there are, in fact, if I put a little count on here because I can't really see, there are, in fact, 20 books that that person reviewed. Isn't that awesome? So you have this cool way to pre-join the most common case, but then you can still ask these broad questions, which normally you would maybe think I need a relational database so I can get straight to the reviews, straight to the user, straight to the books, whatever. Right? So and you saw how easy it is to create these. Like we created 3 tables actually, over here, and relationships and all that, and it was just as easy as typing out the properties. Right? It's a really lovely way to work. So you'll see the reason this is fast, the very next thing we're going to talk about, is I can say, well, why, what are you doing here? You can see that it's using a B-tree cursor called find me my ratings by user ID sorted ascending. Yeah. It's fast because it's indexed. If I take away that index, it is not fast. It's slow again. We could actually probably figure out how slow it is. This may not be a good idea, but that's okay. So first of all, if I run it now, notice it's running, and now it says it's using a basic cursor. That means badness, right? That means we're just going to just crawl across the files on disk or in memory and look one at a time. And so if I take away this and I put a count, I run that, run. It's got a lot of it kind of preloaded, so 600 milliseconds, a little over half a second. But that's more than at least 500 times slower than 0 milliseconds, right? It's hard to divide by 0 because precision's gone, but it's at least 600 times slower. So you'll see that. The next thing we want to talk about is definitely, it's pretty simple, but let's look at indexing. Out of the way. Okay, but my point is, until you get used to working with these things, you'll think this nesting stuff is really cool for the most common use case, but you can't ask general questions. But because you can index down there, you all of a sudden can still ask these cross-cutting questions like you would expect. Okay. Now, the more diverse the types of questions you're asking, the better off you're having a normalized structure, right? If there's one query against this table, well, or this collection, you optimize the heck out of it for that. But if there's 20 different types of questions being asked, it's harder to find one data model that fits. So maybe splitting apart makes sense. Now, there is, I don't know how much we'll even get a chance to talk about it, but there is like a big data Hadoop-like MapReduce style of programming called aggregation that you can use to do cross-cutting concerns and other things that would solve this problem of I've got it structured this way, but I want to ask questions that require me to sort of look across them. Okay, but it depends on what kind of database you're using. Are you building what you would think of as an integration database, right, where there's a bunch of apps using it? Well, this is probably not a good idea for Mongo, which is basically schemaless in the first place. But it also means there's a lot of different types of queries. So this one is probably more normalized. If you're building an application database where you're exposing your data over a service and only one part has control over that database, then maybe this is more focused, right? So when you talk to the MongoDB guys, they actually have an office here in London, and I believe they have what's called office hours. I don't know if they do it in London. They definitely do it in New York and San Francisco, where you can just drop in once a week and ask them any questions. So for free, basically free consulting. I encourage you to go. Only 3 or 4 people go a week. I was doing a training class actually at Mongo, and we took all the people, over the whole week, they had 20 questions. I'm not really sure why they did that. I can tell you what happens, but you got to ask the guy who wrote it why. So they wrote those all down, and we just stormed them. And they're like, whoa, we need more people. Anyway, you can go ask them. And when you talk to them about performance, they'll say, what is the single biggest thing we see people doing wrong with performance? And a close second maybe is document design, but number 1 are indexes. They're just missing. And what you will find out is that indexes are more important in document databases than they are in relational databases. Okay, which sounds counterintuitive. You think you got many, many pieces. Well, I'm going to need indexes all over the place. And I got a document. I just get the document. Why do I need so many indexes? Well, when you break it into all those little pieces, every little piece has a primary key. And every relationship, some sort of foreign key relationship. And by default, you have indexes on primary keys. Whereas, can I go back? Is this reasonable to go this far back? Probably not. So here I have, 15 or 18 primary keys before I do anything? Here I have 3. But I'm probably asking the same questions as I did before. So there's just fewer inherent in the system. So you have to think about putting them back yourself, all right? And that's why you run into questions and problems like this. It probably means too few, but it could be too many if you're trying to write a lot and the write performance is not killing it for you. Now, what you probably don't want to do is sit back with a whiteboard and just think about all the types of queries we might come up with. While that's a great and fun exercise, there's a very empirical way in which you can figure out what indexes you need. You can just turn on profiling and go click around on your web app, and it'll say, these queries were really bad. So you're, all right, well, let's put indexes on those, reset the profiling, click around some more, and go, well, those are not bad anymore, but these are really bad. You just do that until your, what you call your slow query profiling list is empty. Well, as empty as you can get it. You probably can get it empty, depends. For example, if you go over here to our main website, which is a little bit slow, but it's like we were talking about courses. So here's a course on Node.js, and here's a whole bunch of courses about JavaScript and so on. There is not a single query on our website that takes more than 5 milliseconds, and it's running on a pretty wimpy server. That's pretty awesome, right? And the way we got that to work is not because we thought super deeply about it, but we just turned on the profiling and we just started working our way down the list. Right? What is the worst query we possibly have? Let's fix that somehow. What's the second worst and third worst, and so on. So you can be very empirical about this. And you may also want to add other indexes because eventually you want to ask a question, but start by just getting numbers because it's very easy. Okay, so we can turn on this thing called profiling, and I'll show you how to do it. So I can come over here and I can run these 4 statements here. And these slides are available in the app. So you can run that. Let's just go over here. What database do I want to turn this on? Here, I guess. So I can just go over here and run these 4 things, which, let me show you. Turn off profiling, delete the old profiling data, turn on profiling, or create a collection where the profile is going to go, make it capped, which means don't let it grow arbitrarily large because I accidentally left that on in production and now the disk is full and we don't know why, right? Set it to some upper bound that you don't think it's going to overrun. And then say, okay, I want you to only show me slow queries. This is log nothing, that's log slow, that's log everything. So log slow queries, and what do you define as slow? 5 milliseconds or more, that's slow. How many of you guys have databases where you're like, 6 milliseconds, that sucks. We can't have this. Probably not, right? Maybe, which would be awesome. But it's a really great worldview. It's like, 5 milliseconds, I can't be doing more than that. That is wrong. Can we fix this? All right, so let's run this. And if I accidentally hit 5 instead of F5, it hates it. But you can see that it says a few things like, it was this, it was 1. I guess it was already on. So now it's on again. And here it is. OK, that worked, right? It's not super interesting. Basically, it means that worked. All right. So I can go over here and say refresh, and under system, we now have profile, and I can go view the documents. And it says there was nothing there, but theoretically, there will be some things to show there. All right, so remember, this is my book scenario with 250,000 books and 1.2 million reviews of those books. And you already saw somewhere, if I can find it again, not that, not that, not that, not that, not that, that. We saw that this, let's just get rid of the count. We saw that this query took a while, 600 milliseconds. So if I go back over here and I rerun this, it'll go, oh, you now have something that was bad. If we can look at it, we can see, OK, the query was, well, let me go back over here first. Like, notice this part. Curly brace, ratings.userid, object ID, whatever, like that is right. It's like literally right there. That is the statement that was issued to the database. And when you see yourself type it in, it's very easy to correlate these things. But when you're doing like link, and the link transformation turns it into something, and that something is slow, how do you know what that is, right? So this will show you exactly the syntax that got sent, so then you can use that to create your index that will then fix the link statement. It has lots of information here, how long it took, about as long as you saw before, and so on. So here's how we're going to fix this. We're going to go over here. We're going to copy this. I'm going to say, let's go back to the collection where I want to generate the index. And I'll just say ensure index. So let me make this formatted better. So what I want to do is I want to create an index on this, and you don't need to put a value here. You just say 1 or -1, ascending or descending, right? So then I'll say name equals find user by ID. No, find rating by user ID. Make sense? Give it something like that. OK, so when I hit go, it's going to be slow-ish. And it's going to crash because I left this little bit down here. It did not love my token, which is apparently not valid JSON, as you can see. See it running at the bottom? It's building the index, which takes it a while. Right now, the database is fully inaccessible. Well, at least the collection is inaccessible. That might be bad if you do this in production. You can tell it to build the index in the background, in which case it still works. It's still slow until it's done, but at least it's not totally locked up. OK, so now if I go back over here and I hit rerun this, is this got to explain? No. I say rerun, 1 millisecond. Back to good. And if I say explain, you can see B-tree cursor find rating by user ID. Make sense? Yes?
How do you manage these indexes? Because when you initially create a database, you just do it through code. So you
Yes.
write code and the database
Yeah.
creates
That is a
it.
super question. That is a really good question. Let me show you develop.com, how we do it there. So, yes, no, yes. So what we do for develop.com is we host it in EC2 on a Windows server in the cloud, and then we publish to it by coming over here, and I right-click, and I say publish, and I use web deploy, and it uses stuff we built on top of web deploy, but it just pushes the code and then restarts the server. What we don't want to have to do is then make sure we log into this server and do a migration. We want the code to adapt as much as possible. So we built this part over here that says under app start, you've got this is MVC. You've got bundle config, route config, web API config, and we created a Mongo config where we just jam in all the indexes that we find. And every time we find a new one, we put it there, right? And we call this function from app start in the global ASAX. And what it does is it just goes through and it says for each one of these, run this. You could do it in C#, but we want to be able to try it in the shell and then copy it here. And it's just, I don't want to translate it and make a mistake. I just run the JavaScript. So it will just do these. And then every time we find a problem, we'll just put it to this list, rerun the app, and when the web app starts, it'll recreate the index.
Assuming those indexes already exist, then
It's really quick.
it's really quick.
Yeah.
Make a bootstrap one.
Exactly. It would just drag on as it started. But yeah, so this is the ensure index is, if it already is there, just let it be. Otherwise, create a new one. So, almost all the time nothing happens, but periodically we'll add a new index here because we've changed our model so that now we have a different type of query. We need to have an index there or something, and then we'll just let that run. Does that make sense? And this way, when we just publish to EC2, it automatically restarts the server and automatically runs this at app start, just like bundle config and route config and web API config and all that. I'm not sure if this is a good idea or not, but this is what we do, and it's been working for a few years, so we're going to keep doing it, I guess. OK, so let me show you some interesting stuff. How much of a difference can these indexes make? You guys can imagine they're not trivial, right? So let's open up this bookstore app perf after thing. So this is actually from here. Come on, hotel network. From here, our MongoDB class. And what it does is it uses this book database that we've been talking about with the reviews and the ratings and so on. And it does a couple of things. It might make sense to just run it, but let's just look through the code here. So what it does is it first cleans up the profiling, which you saw me do in the shell, but you can do it in C#. It does it here. And then it turns on profiling to 5 milliseconds. And then it just sort of pretends to click around. It just runs some typical queries to ask questions we might ask. And so if you look over here, this is like, find me the books where the publisher is this, and do some projection. Find me all the users in some city. Find me the users who are between 18 and 30, right? These are like typical queries we might run. So, and then what it'll do is actually go into that profiling database and show you, just like I did manually, it'll just pull them out and go, these are the worst, because you can sort them by the time it took. And then it'll actually show you whether or not they're using indexes and so on. And then it'll add indexes and then do that again and show you what happens, OK? So let's run this really quick. I'll zoom in a little bit for you. So here you can see it's like cranking away, running those queries. You notice they're slow. And then it said, all right, let's see the 10 worst. Took more than 5 milliseconds is bad. So it took 510 milliseconds to ask, show me the user here where they have a rating greater than 5. So this, we ask, show me all the ratings by a particular user where they rated it 5 or more on the book. And that took half a second. And then find me just the user, took this amount. Find me the publisher, find me the books by John Grisham, took 160 milliseconds, so on. So now it's paused to just let you think about that. And then it goes, all right, here, these are the answers, and it's using a B-tree cursor. And it took, like you can see, these all are B-tree, which means no indexes. Now it's adding the index, and it tries to emphasize this is going to take like 20 seconds for this to happen. All this you get to take with you. You guys, you can do whatever you want with it. But if you were close to me, you would hear the fan going on my computer now as it's cranking away on it, generating these indexes. And then in a second, it's going to just run that again, and you'll see what you get. So give it a few more seconds, and it should be good. All right. Now it's doing more queries. And now it says, whoops, sorry for bouncing around there. It says, show me all the 10 worst queries. Well, this one took 6 milliseconds. Maybe if I ran it again, it wouldn't. But the first time, it had to retouch it after it sort of dropped the database out of memory. I have to go back to disk. It took 6 milliseconds. That was terrible. Now, if you go back and look, all right, let's ask how many users are over 18? Well, there's that many, and it took 1 millisecond. How many live in Calgary? 0 milliseconds. How many users are between 18 and 30? 11 milliseconds. Ooh, I think that might. I think part of that was streaming back the 63,000 users. How many people live in Moscow? 0 milliseconds, right? Pretty cool, right? So from now on, we're going to look at, let me see what time it is, just so we, oops, control, zoom, this way. Yeah, so now I think what we're going to look at is basically how do we scale this out horizontally, right? How do you do really cool, like NoSQL stuff, as in hashtag NoSQL, right? From the original 2009 meetup where they were talking about that. But before we get there, like, notice none of this stuff I've done has to do with scaling out. This is just taking a single server and treating it the right way. Indexes, good document design, all those types of things, right? So before you go throwing complex network hardware topologies at a problem, start here, right? It's very likely 1 or 2 servers is all you need. Unless you have a massive, massive amount of data, then you really maybe do need to do the stuff we're about to talk about, okay? Make sense? All right, so I'll just flip through this. You guys can download the slides, but it basically says, look, you can explain these queries. You can look at the cursor they're using, how long it took. And if it's B-tree cursor, that means you read along the whole disk. That's bad. So you want a B-tree, not a, sorry, this is basic cursor. If you want a B-tree cursor, you get much better performance. Kind of looks like this, right? O log n versus n or something like that. OK. Let's keep going. You can also use indexes for uniqueness. So if you want the username to be guaranteed to be unique, you can create the index to be not just an index, but a unique one and things like that. OK. All right. So one of the final things that you can do for performance before we talk about scale out is you can issue set-based operations instead of ORM-style operations. This is obvious in SQL, but not so obvious here. But you can issue operations like go find me this book and set its price to that. And you never actually retrieve the book. Right? Or you can say increment its value, and that actually lets you do it like concurrently, safely, and so on. That's fine. Now, let's talk about the interesting part. This is probably what you guys thought we were going to talk about the whole time. But we basically have enough time to talk about it. So I'm on this, in this group from the MongoDB guys called MongoDB Masters, which is kind of like the Microsoft MVP, but for MongoDB. And so there's a lot of guys that do really interesting stuff. For example, some of the people who are the MongoDB DBAs for Facebook, and some of the hosted MongoDB as a service guys, and so on. And they were looking to recruit some people to work with them, so they sent around this message that said, hey, we're doing really awesome stuff with Mongo. Here's just an example of one deployment of what we're doing. So they said, we're doing 120,000 read, write, update, deletes per second on a single cluster. And we're transferring actually 2 gigabytes of data between the database and the app per second. So if you need to scale out, you can scale this stuff out to do amazing things. But like I said, you may not need to, right? You may be able to use what we've seen so far. Right? But what I'm going to show you is how you get to these numbers now, right? So obviously, with non-cluster-friendly databases, you scale up. You get a super expensive machine, and you really hope it doesn't break, right? And you put stuff on it. It's expensive. With these NoSQL ones, they were built to be horizontally scaled. That's one of the primary things they do. So they're much easier to scale horizontally, which is easier to live with, sort of. You can scale farther. It's cheaper. If something breaks, there's easier to put redundancy in there, and so on. So there are actually 2 ways that MongoDB scales horizontally. One of them is mostly for fault tolerance, and one of them is for performance. But it's not that clear-cut, as we'll see. Okay? So the 2 ways are called replication and sharding. Replication is mostly a fault-tolerant thing, but you can also use replication for offloading workloads out of production. Let me give you an example. So imagine I'm running a big e-commerce website, and I've got tons of data in there, and analytics and tracking, and this is all coming in real time, and I need to keep my site responsive and working. I don't want to run like big data type queries that might take 30 seconds or something, just pounding on the server to give me an answer about what are our business trends or whatever. So what you can do is you can use replication to replicate over to another part of the cluster and do queries only against this, but then teach your web app, stay away from the analytics part, only talk to the real part. things like that. So you can use replication for scaling, but its main purpose is for fault tolerance. Right? So what you get is I have some server, one of them is called the primary, that's the one you talk to, but these others are all kind of hanging around listening to it. And if one of them fails, like the primary fails really, if the primary fails, they're going to figure out who is the best candidate to be the new primary. Right? So there's rules about this, like who is most up to date, and you can set them to say this is on crappy hardware, so please don't let it be the master, things like that. But there's a series of choices they make, and they vote, and then one of them becomes the master. This one might come back to life, be behind, wake up, join the replica set, and then catch up and be a secondary. Maybe it'll eventually go back to being primary, maybe not. Make sense? So this is one style of scale out. It's good for scaling reads, potentially, because you can, if you choose to, start reading off of all 5 servers, not of just one. There's consequences of that, but that is one way to scale relatively static data very nicely. But no single query will get any faster. I could have hundreds of these little replica pieces, and if I ask one question to it, it's only going to go to one server and ask that one server this question, and it has to process all the data. Does that make sense? Technically, I think you can only have 12 replicas or 11 or something like that. But imagine, there's no amount of hardware I can add to this to make single queries faster. But if I have 100,000 of them, and they're all individually fast, but they'd overwhelm the one server, then maybe I could scale it that way. Right? So on the other hand, suppose I have 200 gigabytes of data, and I want to ask interesting questions about it. Sorry, I'm out of my box. Forgot, I'm supposed to stay in my box. So what I could do is instead, I could say, look, let's get 20 servers, 5 I guess here, 5 servers, and we're going to put a little part of it on one, a little part of it on the other, 1/5 basically, not exactly, but we're going to try to evenly distribute our data across those 5. And when we ask a question of Mongo, I want to parallelize the processing of that onto all 5 servers. They all sort of individually come up with the answer, and then they report to this sort of intermediary that pretends to be a regular Mongo, but is actually a Mongo S for shard server, as opposed to Mongo D for Mongo daemon. And then that thing's job is to correlate the answers and then return them. Okay? So this lets you scale individual queries. So if I've got 200 gigabytes and I ask a question and it takes 30 seconds, I want it to take 3, that would solve it, maybe, right, if you do it right. It has the potential to solve it, where this never has the potential to solve that problem. This also scales writes. So if you were doing like tons of analytics and data was just flying in or whatever, one of the more interesting uses of using Mongo is CERN. The Large Hadron Collider uses Mongo to capture the particle data as the collisions happen. Right? So maybe there's tons of data coming in, like, whoa, let's grab it. So you could throw it into something like this, and basically all of those disks can be writing and generating the indexes and so on, which would be faster than writing to one and then copying it to the others. So you can definitely scale writes that way. You can speed up individual queries, and you can kind of offload some of that to the other pieces over there, so reads can get somewhat faster. Right? If they're all somehow hitting the same server, it's not going to make a difference. But if they happen to somehow to be distributed in a decent way, then that would speed that up. Whereas this is only about increasing read performance. All right? We're going to look at this in some detail because it's complicated. But questions before that? Yeah?
How would disaster recovery or your redundancy fit into sharding?
Great question. So this makes you more fault tolerant, right? That actually makes you 5 times more likely to lose data than if you didn't shard at all, right? Because if there's a 1 in 1,000 chances of one server dying, there's 5 in 1,000 chances of one of those servers dying, yeah? And if one part goes down, so at least some of your data is toast. You can make each one of those green boxes a replica set, right? So that each individual box over there is fault tolerant on its own. But only use this for fault tolerance, right? Don't do any other magic I was talking about. But maybe put 3 servers under each square over there, and then you've more than enough time to react to problems. Make sense? Of course, all of this adds complexity. If now all of a sudden you're sharding to 5 servers, and each one of those 5 servers is really 3 that are all like, it's just not as simple as dealing with one. There's ways to deal with it. So they've got like management services that you can do to like look at your cluster and stuff. But it's, you know, if you go down this road, you are choosing a more complex story than if you were able to make one server fast. So just a warning, right? All right. So let's look at replication really quick. I think sharding is pretty straightforward. What you do is you go to the collection. You say, please shard this collection across these servers. And use this key, like username or state, country, or whatever, as the key to do the sharding. And then it's done, right? It's off and running. On the other hand, replication gets there's a lot of switches over here you can throw. So let's look at that kind of quickly. One of the questions that came up yesterday, and it's worth bringing it up, is what happens with sort of eventual consistency in MongoDB in general? Well, first of all, if you have one server, there is no eventual consistency. There is a server, you wrote to it, it's written. You asked for the data back, it was there. Just like SQL Server, it uses journaling, all that kind of stuff. Once you start down this path, it can get more complicated. So again, the sharding story, there is no eventual consistency. You wrote to it, it's written. It won't tell you it's written until it is written. And then you get a response from the database driver in your code, and you know it's written. Right? Over here, by default, you get strong consistency just like SQL Server or Oracle or Mongo by itself. And that's because they only let you read and write from the primary, and then these are here for fault tolerance. If you go to your connection string or other areas and configure it, you can say, I would like to also read from these secondaries. Then it gets more complicated. But unless you make effort to do so, it will only read and write from the primary, which means there is no eventual consistency. There's only strong consistency, which means you don't have to think about any of this, right? Which is great. If you have to start juggling inconsistencies, all of a sudden your app becomes more challenging, yeah? So how does this work? Well, these guys tail what's called the op log. And they all have op logs, not just the primary. They all like look at each other. So they listen to the op log, and every time an operation happens on the server, it puts a little record in there. These guys replicate that over here and replay it against their data. Of course, they start by synchronizing all their data, then playing the op log. So records in there look like, hey, at this time, I did an insert, and it uses I, so it can minimize space and all, against this collection, and I inserted this object. So please redo that to your data. So basically, whatever happens to the server is replayed against the secondaries. So they should be consistent, right? So it looks something like this. You make a change to the primary, it updates its collection as well as the op log. This guy replicates it and then just reapplies it. Right? So there's also a heartbeat that goes between all of them. And if a majority of the secondaries can no longer find the primary, they're going to think that it's dead. Right? So this has like a 10-second delay if you were to shut off the primary until they've really decided it's totally broken and we're switching. You can change those numbers, I believe. You can also have what are called arbiters, which are other instances of Mongo that just watch it. They don't have to hold any data. They could run on like a really crappy VM or something. But their job is to just watch and vote so that, you know, if you don't have enough real servers, you can do something. So imagine that the top one can't find it anymore, and after a while, 10 seconds by default, they decide, actually, this bottom one is now the primary, right? You also have to adjust your connection string to make this work. So you start the servers with a replica set command line argument to say you're all part of this replica set called X. And then you connect, you have to do a little initialization in the databases as well. And then when you connect to them, you want to say as many server names as you can, because what if you just said server 1 and that was the primary, but if it dies and then you try to connect to it, how are you going to figure out who's now the primary, right? So this way it'll just like talk to any of them and then ask them, okay, you guys, which one is the primary? And works on. Okay. So by default, like I said, it only reads and writes from the primary, which gives you strong consistency. You can give it these other options. Read from a secondary only. Prefer to read from the primary nearest. So what I could do is I could set up a replica set with the main server, I know, in Ireland, and then one replica over in US West, one in US East, one in Asia, and then I could have web apps running all these places and say, read from the one closest to you. And they use the universal internet metric for distance, ping time, right? So whatever one is like the closest on the network in ping time, that's the one I'm going to talk to when you say this. So you can use it for geoscale. That's kind of interesting. You can do this on the connection string. You can do this on an individual database, all sorts of stuff. So by default, what you get is strong consistency or strict consistency, just like you get with SQL Server, and that's great. Now, if you're going to step out of that model, where will you land? You probably don't want to land in the red. Like imagine you're writing something super simple like a bookstore, and you can review your book, a book. So you go in there and you type in your review, and like, this is the first book I've ever reviewed, but I so loved it. It just made me feel like when I was a kid, you know, da-da-da, you write like your whole life you put into this thing. You hit save, and you refresh the page, and your review is not there. You're like, no, where'd it go? And you refresh again, and of course it comes back. You're like, oh, that is such a bad website. If someone else looked at that thing right as you hit save, whether or not they saw your review, nobody cares. But if you don't see a review, then really frustrating stuff happens. So you want this probably read my writes level of consistency at least, or you've got to do lots of work to make it, you know, you've got to make it slow enough so that the page doesn't refresh, you know, like weird stuff that you don't want to do. So you can do that by basically encouraging, I'll show you. You can set this thing called the write concern. So by default, you read and write from here only, and that's always consistent because that's one server, and it eventually replicates over here. If you turn it to read from secondary and you don't do anything else, you might write here and then immediately on the post back read from here, and then 100 milliseconds later it replicates over here, but it's too late. Your little review is gone, and you're mad at Amazon.com or whatever. Okay, so that's a real concern. What you can do is, as part of your connection, you can say, I do not want you to return from the save method until you have replicated this data. So don't even tell me it worked. Don't even let my program continue until you've replicated this data. Right? In that case, you save, you wait for a little while, maybe a little longer, and then you post back redirect, hit this, but the data is already there because you said wait until it was there. Make sense? So you can sort of scale out reads that way in a read my write level of consistency. Now, you actually give up something when you do this, because you have to say how many replicas you're going to wait for. In this world, I could have 5 replicas. 3 of them could die, and who cares? We still got the main server and 1 more replica. It's great. On the other hand, in this world, I have to say wait for how many replicas there are. And if one of them dies, well, I'm going to be waiting forever. Right? So you're giving up this fault tolerance to scale these reads. Right? So I'm not necessarily recommending this, but it's something you can think about doing. All right. So here are some of the write concerns. -1 means like fire and forget. Unacknowledged means just as soon as the network socket opens, just tell me it worked. Acknowledged as the default is wait till it's put in at least to the journal of the primary server and in memory. And then you have these other sort of knock-on effects. You set this up at the database or on a single operation. You can also, like I said, use what they call tagging for tagging plus hidden replicas to do sort of secondary services. So maybe your replica is fast enough on its own just to run the website, but then if you're also going to do backup off of it and you're going to do big data, sort of analytics, like aggregation, MapReduce, then that thing is going to die, right? It's just too much. It's like near its limit, but it's not too much yet. So you can actually replicate out to other areas. Like I can replicate over to this server for analytics and tell that guy, that website, to stay away from this. Don't actually write to it. Pretend it's hidden to the client, but it still is participating in the data replication. And then you can just run queries against that. You can also do that for backup. Don't actually query the backup server, but let it stay. Like maybe that's an off-site disaster recovery type story, right? It's always replicating over there, but it's on crappy hardware. Please don't, and it's far away. Please don't try to actually use it as the primary, things like that. Okay? So you have a lot of interesting choices that are a lot of switches you can run here. All right, so what did we talk about? We said, look, you want to choose the right kind of database to work with. My current working theory from experience is document databases are probably the most generally useful. Then probably relational, and then the other crazy ones like graph databases and so on. And I already talked about why MongoDB is a pretty good choice. It's definitely the most popular. There's a lot of libraries to work with it. There's a lot of people with experience on it and so on. And then we looked at 4 things to make it faster. Obviously, document design is super important. So you want to think about, just when you get started, how that works. It's not strictly a performance thing. You have to do it just to even use the app. But it has an impact on performance. And then indexes, turn on profiling, click around in your app, see what was slow, fix it with indexes, repeat. You can do in-place sort of set-based operations. If you've got a 1 megabyte document and you just want to increment a field, you can just issue an increment statement without pulling the whole thing back, changing it, pushing it in, so on. And finally, we saw we have sharding and replication as the 2 scale-outs. And of course, they can combine so that you have replicated sharding or something like that, whatever the term would be. All right, questions, comments? Yes? So you have replicas on the, indexes on the replica set. Yeah, uh-huh.
So if your main application is talking to, say, 3 of them, and then you've got something else and you've had one up with reporting, you have the reporting one.
Have additional indexes?
Yeah.
That's a good question. I believe the answer is no. It seems like you could connect to it and just say, I'm just going to change you, and add an index, and it may accept it. But, they do have, I've never tried it, but they do have the rule where you're only allowed to write to the primary ever in the replica set, right? So there's no option to change. I want to write to the secondary. It doesn't do like peer-to-peer sort of stuff. There's like somewhere where you write and then it replicates, and you may or may not read from those replicas. So I think the answer is no, but it is a good question because it would be cool to have that. Because you might want more indexes where you're doing analytics and very, very few where you're writing it because you want to write as fast as possible, right? Okay, yes?
How do you manage security with this?
So how do you manage security? There are users, groups have permissions. You can do this at the database level, and you can do it at the server level. So I could be a server user but an admin of a database. I don't know for sure. I don't think you can set collection level rights. I think it's only at the database. They are looking at, in the next version of Mongo, of having more fine-grained permissions. So for example, you're not allowed to read social security or credit card number or something unless you're this type of user. But you can write it or something like that, But right now, it's basically, there's a bunch of roles about what you can do and see, and that's at the database and server level. Let me think. Yes, one more thing. You can do encryption between the app and the server, right? So this is important. If I put this in the cloud and I'm running locally, you would like to not share your data publicly. By default, what you download from mongodb.org does not do encryption on the wire. But they have an enterprise version, which you can buy, that does encryption. Any of the cloud-hosted ones have encryption. And if you download it and recompile it yourself with the right flag, that will have encryption. But they're an open source company, but their business model is trying to upsell you a little bit. So SSL on the wire is one. I only bring this up because if you think that's the default and you just drop one in a server somewhere else and you talk to it remotely, that might be a big problem. So just be aware, right?
What protocol gets used to talk between the client?
It has its own protocol. is it on top of HTTP or TCP? I think it's just TCP. There is a REST API you can enable, but it's off by default. So then there's an HTTP protocol. But I think it's just its own serializing BSON commands across. Anything else?
Am I naive? I'm not using MongoDB, so I'm very naive to NoSQL. But I noticed in the Rover Mongo stuff there was no support. I couldn't see any store procedure or trigger.
So what's the storage procedures and triggers? I'll show you that really quick. So over here, well, let's just go to this one. It's already running. Over here, they do have functions, and I can add a function, which is a JavaScript function. So that's like a store procedure, right? There are no triggers. Yeah. The trigger would have to be something in your app. You'll find a lot of the stuff that you would think of putting in the database kind of moves to your data access layer, and you have to enforce it through like a little one step up the stack. Which, yeah. Now, let me point out one thing really quick. You guys saw me write some code up here, and that was pretty cool. I hope you enjoyed that. I want you to have it, so here, let me do this. Final demo from SA 2014. Commit, sync. So if you go over here to GitHub/Mike, C as in Cat Kennedy, you will find, among a silly picture of me, a thing called presentations. And in presentations, you will find conferences, SA 2014, high performance NoSQL, and this is the stuff you just saw me write, right? So here's the indexing one with the bookstore. Here's the design books that you just saw me write. Right, okay, so it's already checked in. If you want it, just go clone it or download it, whatever, right? Okay, so time is officially up, and you guys stayed 2.5 minutes late on the final presentation, so thank you. And thanks for coming. I hope you guys got a lot out of it. If you have more questions, come see me afterwards, okay? Thanks.